What specific problem does your method aim to address in the context of transformer architecture and propositional logic?
Our method aims to address the unclear mechanisms within transformer architectures that enable them to perform reasoning and planning in propositional logic problems. Specifically, we investigate how transformers internalize and plan for solving simple propositional logic problems, such as determining the truth value of a query based on given rules and facts. By conducting experiments on both shallow transformers trained on synthetic problems and a pre-trained large language model, Mistral 7b, we uncover the specialized roles of attention heads and the routing signals that guide the model's reasoning pathways. Our findings reveal how the model processes context, locates relevant rules, and makes decisions without relying on chain of thought, thereby enhancing our mechanistic understanding of reasoning in transformers. Ultimately, this work contributes to the broader field of mechanistic interpretability by elucidating the internal circuits that facilitate logical reasoning in these models.
Can you explain how the proposed method works? Illustrate the algorithm step by step, particularly the role of the routing signal and how it influences the attention head's behavior.
The proposed method involves a systematic analysis of how transformers, specifically a small GPT-2-like model, process propositional logic problems. The algorithm operates as follows. First, the model receives a query token that determines whether a linear or logical operator, log-op chain, is being queried. At this point, a routing signal is generated in the Layer 2 attention block, which indicates the type of chain being queried. This signal influences the behavior of the Layer 3 attention block. If the routing signal is positive, the Layer 3 attention focuses predominantly on the query position, effectively passing the information directly to the answer position for linear chains. Conversely, if the routing signal is negative, the Layer 3 attention shifts its focus to the rules and facts sections, allowing the model to refine its answer for log-op chains. This routing mechanism is crucial as it dictates the attention patterns and ultimately the model's output, ensuring that the correct reasoning pathway is followed based on the type of query presented.
Can you walk through a simple example demonstrating the inner workings of your algorithm, using a specific logic problem as described in your paper?
Certainly, let's consider a specific logic problem from our paper. Rules K implies D. D or E implies A facts. K is true, P is true, V is false, query A. To solve this, the transformer first identifies the query token A, which indicates that it needs to determine the truth value of A. The model processes the context by utilizing a routing signal from the Layer 2 attention block to inform the Layer 3 attention block, whether it is dealing with a linear or logical operator, log-op chain. In this case, since the query involves a logical operator, the model focuses on the relevant rules and facts. The first two layers generate a partial answer by passing relevant information about K, which is true, to the third layer, which then refines this information to conclude that A is true, as it follows from the rule D or E implies A. This demonstrates how the model constructs a reasoning pathway from the rules and facts to arrive at the correct answer without using chain of thought, COT.
What are the main theoretical or practical benefits of using your approach compared to existing methods for reasoning with transformers?
The main theoretical benefit of our approach lies in its focus on mechanistic interpretability, which allows us to uncover the specific internal circuits and mechanisms that enable transformers to perform reasoning tasks, particularly in propositional logic. By conducting fine-grained analyses on both shallow transformers and a pre-trained large language model, Mistral 7b, we identify specialized attention heads that play crucial roles in processing rules and facts, thus providing insights into how transformers internally manage reasoning pathways. Practically, our method of activation patching enables us to isolate and evaluate the contributions of different model components, leading to a clearer understanding of their roles in reasoning tasks. This contrasts with existing methods that primarily benchmark performance without delving into the underlying mechanisms, thereby enhancing our ability to design more effective models for complex reasoning scenarios. Ultimately, our findings can inform future developments in transformer architectures, making them more adept at handling intricate reasoning problems.
How did you validate or test the effectiveness of your method? And what datasets or benchmarks did you use to measure performance?
To validate the effectiveness of our method, we conducted experiments on two types of models: shallow transformers trained purely on synthetic propositional logic problems, and a pre-trained large language model, Mistral 7b. For the shallow transformers, we achieved 100% accuracy on the reasoning tasks, allowing for a fine-grained analysis of their internal mechanisms. In the case of Mistral 7b, we focused on a minimal version of the reasoning problem, where the model was tested on 6 in-context examples, ensuring that the first answer token was unique and the truth values were constrained to maintain the challenge. We employed activation patching and causal mediation analysis to uncover the roles of specific attention heads and their influence on the model's reasoning process, confirming the significance of certain components through interventions that altered the model's predictions. Overall, our approach combined controlled experiments with targeted interventions to assess the reasoning capabilities of the models on the propositional logic tasks.
What notable results did you achieve with your method, specifically regarding accuracy and the insights gained from analyzing attention heads in the transformer?
In our experiments, we achieved 100% accuracy with shallow transformers trained solely on synthetic propositional logic problems, demonstrating their capability to solve these reasoning tasks effectively. Through our analysis of attention heads in the Mistral 7b model, we identified 4 specialized families of attention heads: queried rule locating heads, queried rule mover heads, fact processing heads, and decision heads, each playing distinct roles in the reasoning process. Notably, we found that the queried rule locating head is crucial for identifying the relevant rule, while the decision head consistently focuses on the correct starting node and variable, indicating that it already possesses the answer. Additionally, our interventions revealed that the routing signal at the query position significantly influences the model's reasoning pathway, determining whether it processes a linear or logical operator chain. These insights enhance our understanding of the internal mechanisms that enable transformers to perform reasoning tasks without relying on chain of thought.